Hello everyone and welcome to another ECT Star meeting. Our seminar this week is by Hilla De Leon on the very timely subject of vaccine effectiveness against COVID-19. Hilla received her bachelor's in physics and chemistry in 2006 from the Hebrew University of Jerusalem and her master's from the Weizmann Institute of Science in 2009. She earned her PhD in 2018 at the Hebrew University of Jerusalem with the thesis on electroweak transitions in A=2 and 3 nuclei in pi-unless ECT under the supervision of Professor Doron Gazit. Hilla remained at the Hebrew University for another year as a postdoc, and then in 2019 she came to Trento as a TIFPA ECT Star postdoc. So, with this short intro and without any more delays, Hilla, the stage is yours.
Thank you, and thank you everybody. And this is going to be a bit different seminar, I think. It's going to be very on the subject. And my main thing that I want to show here in this talk is actually how we can take a very fundamental, very theoretical physics, which we all do, and how we can make it more applicative and something that is actually related to lives of a million or even milliards of people. I will start by sharing. I can share my screen, right? Okay. Tell me. Yeah. Do you see the screen?
Yes.
Yeah?
Yes.
Yeah, the very, very lovely Trento. So actually, I'm going to start with nuclear physics, which what I did in my PhD. Just a sec here. So in my PhD, I, as was said, calculated low energy transition in a very light nuclei, 2-body and 3-body deuterium, helium-3, and triton. And we did a very nice work showing a very good agreement with experimental physics. And for example, calculated magnetic moments, the PP fusion, etc. And when I finished my PhD, my main question was, I used pi-unless ECT, which is a very nice effective field theory, which is good for very light system. How can I extend this very nice theory to many body systems? So I came to Trento working with Professor Pedreva. And what we did, we were able to extend this theory to very large system. We started with 4-body, moved to 10. And what we did what a lot of us are doing. Actually, we do a quantum Monte-Carlo algorithm. So we solve the Schrödinger equation. Oh, sorry, I don't know why it's moving. We solve the Schrödinger equation for a many-body system. We use 2-body and 3-body potential regulated by a high ultraviolet cutoff. We did it for 4-body, 5, 6, 7, 10, and then moved to 100. And we showed that the pi-unless ECT can be used to describe even many-body systems. And when the COVID-19 started to spread all over the world, I asked myself, what happened? It will take the same mechanism of doing, I don't know why it's moving, I'm sorry, doing a Monte-Carlo with a 2-body interaction regulated by a cutoff or ultraviolet cutoff in order to predict the spread of the virus. The same mechanism for many-body physics, which was bosonic system, and now just spreading of a virus. So what actually we do that we think of infection probability, where for each healthy person can become sick with on a basis of a daily probability, which is a sum of all the sick people all around it. And what we use is what we call the one-way Ising model, in which a healthy person can become sick by interacting with a sick person, but not vice versa. You don't become healthy by being around healthy people. And we use the very general principle of a Brown motion in which all the population in our area has a displacement dominated by dr, which distributes normally, and it's related to what we call the diffusion constant. And we know that there is a relation between the diffusion constant and what we call the mobility. As you can see here in the movie, I have two kinds of particles. I have the little ones and I have the big one. And we can see that the little one moves much more faster than the big one. So we can say that the little one has much higher mobility than the little one has much more mobility, higher mobility than the big one. And we can think of that actually by thinking of temperature, because the diffusion coefficient is a multiplication of the mobility and the temperature. So if we fix the temperature, the only thing that we have is the mobility. But an alternative, we can fix the mobility and then think of the system as a heating or cooling system. And here we are talking in terms of mobility, where in terms of the spreading of the virus, high mobility is time where everybody can walk freely, no restrictions, no lockdown, actually what we had 1 year ago. And when we started to work on this model, we had to do a lot of data. We had to dig into the data. So we contacted with a group from the Weizmann Institute, which kind of worked to summarize all the epidemiological data knowing about the virus, because we have to take into account how much time a person can be contagious, when a person can develop symptoms, and how many people in general one person can infect. And actually all of that is summarized really well in this website. And we wrote a model taking into account a lot of parameters, kind of summarizing into a probability of infection. For example, what is the distance in which a person can infect another person? How long it takes you to develop symptoms? If you have no symptoms, you are asymptomatic, if your transmission is lower than people that will eventually develop symptoms. How many times a person, for example, how many people one person can meet in a specific day. We know this is vary from different people. And how many people actually are in your house, because we know that you can infect your households. This is also something that you take into account. Do we have or we don't have infection from unknown sources, etc., etc. It's all kind of summarized here. And we started with in our first model to see how a lockdown will affect the spread of the virus. So we checked different scenarios. In all of them, in the first 14 days, again, this was in March, almost 1 year ago, when everything was very fresh and we knew literally nothing. So we assumed that in the first 14 days, you have no restriction, it's just the beginning of the spreading. Everybody will walk freely. And then from day 15, you have a very full lockdown, which was in Italy, in Israel, and actually all over the world in March and April. And then we checked what happened when you open the lockdown. And by doing that, we assume that in that time, people will wear masks, supposed to reduce some of the transmission of the virus. And we checked in the beginning 4 different scenarios different scenarios of model. And what we changed in the model, we changed the mobility. So in the first model, we opened the lockdown and then everybody can walk freely, again, wearing masks. In the second model, we checked what happened when we have a week pattern, like week with full restriction and week without no restriction. And in the third model, we checked what will happen if we have 2 weeks lockdown and then 1 week no restriction, and then go on until infinity. And in all the models, we checked what happened if we force or not force people to keep a social distance, like keeping 3 or 2 meters from each other, which is kind of the big advantage of the model, because we are dealing with a particle model, it's really easier to us to check specific scenarios. And in our model, we don't use R as an input, the reproduction number. It's actually the output of a simulation in contrast to SIR. What we can do, we can check what is the doubling time of the number of infected people, the function of time. And we know that there is a relation between R0, the basic reproduction number, to the doubling time TD. And what we did that we checked this relation, and we know that without no restriction, the corona has a R0, which is varied between 2 and 4. And then we try to see what is the meaning of R0 in the terms of our model. So what we have in the model, we have a specific area in which we have a density of particles. And we found that the density of the particle is related to the doubling time, in which that the more dense the system is, the lower the doubling time, which actually makes sense. It means that you have more infections and you have, then R0 is much higher. And we checked what is the density in the terms of the simulation, which is equivalent to R0 equal 4 or doubling time of 2.5 days. And we found that in that terms, this is related to 11,000 households, because we check the simulation in terms of household, because we say that no matter what, you cannot, you still have infection in the family. With lockdown, without lockdown, this is something that you can control on it. And then we started, this was our first paper, that we checked what happened for different lockdown scenarios. And this is the error bar originated from the fact that we do a Monte-Carlo and we have different simulation. This is a mean of 100, I think, simulation. And here we have, for example, the case in which we don't have an infection from unknown source. And here we have infection without unknown source. But in that simulation, for example, we forced people with symptoms to stay at home. We want to check how the spread of the virus will change if everybody with symptoms will be home, which we know it's kind of preventing 1/4 of the infections. And already we can see here that the weak pattern, which is the dashed line, just a second. You see here when I do the pointer? Yeah, okay. We see here that the dashed line, the weak pattern, is not very effective. But from the other hand, the weak no restriction 2 weeks lockdown is much more effective. And we did the same with unknown sources. And if we really compare the week lockdown pattern to the 1 week, 2 week lockdown pattern, this is one thing that we found, that in order to control the spreading of the virus, an effective lockdown should last at least 2 weeks in order to see some, as you can see here, some effective decrease in the spreading of the virus because of the epidemiologic nature of the virus, because it takes time to develop symptoms and take time to a person to infect another person, et cetera, et cetera. And that was a very theoretical game, I can say, that we did back in July. What happened now is that we have a vaccination in the game. And as you can see here, I have 2 kind of nice picture. The left one is to get the vaccine, because we actually encourage people to get a vaccine. So here it says that if you are over 18 and you will get a vaccine, you will get a pizza, a beer, an exercise, and you can get a laptop. And in the right-hand side, you can see the amount of vaccine per person all over the world. And you can see that by far Israel is the most vaccinated country in the world, which actually enable us now to do a lot of research and have a lot of data to say how effective is a vaccine based on the real data from Israel. So as I said, in December, in the end of 2020, there was starting a vaccination, but also, which is something that we took into account, we know that we have more and more evidence of reinfection. So in our second work, we're kind of trying to see how these two new facts or will infect the spreading of the virus. So we started here, again, by doing the relation between the density and the doubling time, but now we know that the game was changed. Most of the world is not going around R equal 4, where the virus is spreading, but much, much slower. So now we think that the doubling time, even when we have a spreading, it's around 10 days. So we have to take a much more dilute system, which is good, which means that the spreading is much, much slower. And what we did in our second work was to see how the rate of the vaccination of a population will infect the spreading of the virus. And we did assume that if you were infected, you can be infected again after 150 days. In this graph, for example, we assume that the vaccine is only efficient for half a year. And we checked what will be the spreading of the virus for different rates of vaccination, taking into account that you have to take 2 doses. It means that if you vaccine, for example, 1 million people per day, only half of them will be protected because you have to vaccine double the people that actually are protected. And here we were starting to vaccine in the middle of the spreading, in the 100th day. And we can see very good from the graph, you need to have kind of a high rate of vaccination in order to control the spreading of the virus. And we wanted to see how the efficiency of the vaccine matters to this, how it affects this graph. So we did the same, but instead of 180 days of effective of the vaccine, it's now 2 years, which is equivalent to infinity in our simulation. We can see for now that it does not have much more effect. And if we really compare the two graphs here, we can see that the main effect of how the spreading of the virus will become is from how fast we can vaccine people and not how effective the vaccine is. So, yeah. So until now, it was very theoretical. About 2 months ago, I was asked to help using that model to predict the real data in Israel based on what's happening now. So in December 2020, the Israeli state has started to vaccine massively all the population from age 16 and up. They started from the elderly, age 60, and then went to 50, etc., etc. And you can see from the graph that from now, we have nearly 90% of the population, the elderly population, above 60 is already vaccinated, which is really good. So based on that, we have really real data going from Israel. So for example, in this graph, in the upper panel, you can see a real data from one of the, I don't know how to call it, like a group, have a lot of data. So how the numbers of vaccinated people, elderly vaccinated people, is a function of the time left from the vaccine. The green one is the new cases, and the blue one is the new hospitals. And we can see that there is a decrease as a function of time. So the longer the time left for being vaccinated, we see less cases of new confirmed case and less cases of new hospital case. And in the lower panel, this is the Pfizer, because for now, all the vaccination is done by Pfizer vaccine. And you can see here, this is the data from the Pfizer experiment. And they claim, the guy who did the experiment, that there is no overlap between the data. They said that the vaccine efficiency is much, much slower than what Pfizer claimed. Here is the official data from the Israeli Ministry of Health. You can see here in the lighter blue is the amount of people, the elderly, having the first dose, and then in here, in the more dark blue, we have the numbers getting the second dose, and this is the daily new cases for the elderly, and we can really see a drop in the elderly cases. So this is, for example, one evidence of the efficiency of the vaccine. And they did it's the same, I'm sorry. Okay. So what we did in our work is we tried to compare the different age group. You can see here the upper panel is the effective reproduction number, RE, for different age group in Israel. And you can see that the pink one, which is the elderly, dropped much faster than the other group. And from here, all the time stays below 1. And if we look on the same graph, but in the lower panel for the severe and moderate cases, the new hospitals, we can see also the same behavior. That the elderly was over 1, and then we can see here a drop in the middle of January. And all the time it's less below 1, which we cannot say on the other age group. What is actually interesting that we see that the next group, the 50 up to 59, has now the same behavior. And we know that the vaccine started like 2 weeks after the elderly. So which is a really good evidence for the fact that in general, the vaccine is working, but we want to know how much. And for that, we need a model. So what we did is that in Israel, we had 2 waves of spreading of the virus. We have 3, but now we're talking about the second and the third. We have a big wave starting on September, and we have a wave on January. And we found that the behavior of the 2 waves were very, very similar. So in general, we expected that without any vaccination, the behavior of the new hospitals cases will be the same. But what we found that there is a gap, shift of 8 days of when we had a peak in the new hospitals in the second wave, which you can see here. This is a red curve, to the blue one, which is what happened in the third wave when we have the vaccine. So we wanted to see if we can write a model using the efficiency of the Pfizer that can explain this gap of time. and the Monte-Carlo simulation. Let's hear. The red dots are the real data. Anyone has a question? The green curve is we take into the account that we have some efficiency of the vaccine in preventing infection, that the vaccine really prevents morbidity. And in the blue one, we assume that we have only 50% protection in morbidity. And what we have in the pink one is what we had in the second lockdown. And we found that the gap between the green curve and the pink one curve is exactly 8 days, what we had in the real life. So it's really good for two things. First of all, it's saying that the model is very accurate. And second, it's saying that we can actually evaluate the efficacy and efficiency of the vaccine using that data. And this is good because it enables us to predict what happens if we open. Now, all this time, we had kind of a lockdown in Israel. And the main question being asked is when we can be back to normal life, or how can we have culture and, going back to normal using vaccine. And this is what we have here. We have 3 opening scenarios for severe and moderate cases and for new confirmed cases. For the case that we have a very light opening for what we call R equal 1, 1.2, which is what we had with some restriction. What will happen if we open such that R without vaccine will be equal to 2? And what will happen if we open and R will be kind of a higher to 2.5? And we can see that the vaccines are effective up to some level, because for example, in Israel, we have 35% of the population is under 16. So we have a very high part of the population that cannot be vaccinated. This really affects the exit scenario and how we can open now, even when we have a lot of the population being vaccinated. And I want to finish actually with that slide, because here we have, this is again a theoretical slide, saying what happened if we have vaccine and then we change a temporal change in the restriction, which is equivalent to a temporal change in R. And as we can see here, that during vaccinating, having not control opening will cause to a very uncontrolled spread of the virus. So it means that we have to be very smart when we open, even with vaccine, so not to have uncontrolled spread. And if we want to summer, then we can think of the spreading of the COVID as a many-body problem with an effective 2-body probability to simulate different scenarios. And even though it's really challenging to simulate every scenario, we do see that wearing mask and strict social distancing, and if we don't have a vaccine, then lockdown or a cyclic pattern of lockdown can help keeping the infection under control. And by combining a relatively high rate of vaccination, which has to be accompanied by a social restriction, that can lead to the end of the pandemic, hopefully, in a few months. Thank you.
Thank you, Hilla, for this very informative talk. Are there any questions?
I have a question. Sorry.
Yeah. Well, thank you, Hilla. Very, very nice presentation. I have a very maybe basic question. At the beginning, you showed that in order to model your, let's say, interaction, for saying in a way, you have to use quite a large number of parameters. So I was thinking whether you had the chance to study the sensitivity of your results to the variations of those parameters.
Some of them, yes. For example, there is some that we change, but in the end, we want to fit the parameter to a specific scenario. For example, specific R. So we kind of play with the parameters to have a specific R. But yes, for example, here, in each curve here, for example, the long dash line or the short dash line is the same simulation, but without extra distancing. And this is something that we want to see how that affects the simulation. We want to, for example, what happened if you force people to the symptomatic people to stay. This is a thing that know that we have a lot of parameters, and the main thing, actually kind of like an SIR model, is what will be the doubling time in the end of the simulations. Because mostly now when I have to fit to a real data, I need to reproduce the real data in Israel. So it's less important how I get to this number, it just has to be stable. Okay?
Yeah, actually, yeah, I missed some part because of the connection, but I think I got the message. So yeah, maybe my question was whether you were able actually to determine the most sensitive parameters and also actually following to this.
So the most sensitive parameter is the density. Because what I'm doing now, I'm doing very delicate work. I fit the notice density, it's actually equivalent, the size of the surface in which the simulation is running. I have a connection between R, the real R that was in Israel, to the size of the surface. So I changed the size of the surface in few percent in order to reproduce, for example, R equal 1 or R or lockdown, to get a very that I can reproduce the numbers. So the density is a crucial thing. Yeah.
And just as a following question, whether actually it's feasible for you to model the presence of variants, which actually impact the parameters like effectiveness.
So yeah, when we take into account what we call R equal to 5, this can be equivalent to either a very large opening or a presence of the variant. For example, the British one that is translated to a much higher infection. Because in the end, what we have in the number is R or CD, right? But yes, this is correct. But for example, yes, but again, with changing the surface, then the density is equivalent to, for example, having a variant that infect more people. Yeah.
Great, thanks.
Hi, Hilla.
Okay.
I have actually a question about this slide that you are showing at the moment. Can you hear? Sorry. So
I'm hearing. This is the lockdown.
So basically here you put these restrictions, which means I think the lockdown, but you also comment this SD, which I understand it is social distancing. So which is actually the difference and how this is actually taking into account in the model? So what are the differences?
Okay, very good question. So there is two things. The mobility is, for example, I have two particles. How much the particle can move in a day? This is a mobility.
Mm-hmm.
Okay. Social distance saying that if two particles are close enough, I force them to be apart for 3 meters.
Okay.
The mobility is how fast are you moving. Social distance is how close we are.
And this social distancing means that it will be just less probable for this particle to transmit the virus from one to the other, no? Or
yeah, again, yeah. But we do found that this has, for example, much less impact than the fact that people with symptoms are not seeing anybody, for example.
Mm-hmm. Okay, thank you.
I'll have one question myself, if I might.
Sure.
Okay, thank you. It was very interesting presentation. Thanks. Just this general question. So, if I understand correctly, your model, you're basically mapping the shear dynamics on a Ising lattice, basically.
Yeah.
So, have you considered using? You could do the same with different populations, either because there is older people who are not going out from home and so have little interaction with the others, or because they live people who live in different cities. If I understand your model correctly, that should be relatively easy to implement simply by inserting some quench disorder, taking into account the intra-group communication and the intergroup communication. Is that right?
Yes, you're definitely right. I did that. I know you can do that. For example, I can also think of what happened if I have, because in Israel it's really interesting because we have, for example, a different society groups. We have the ultra-Orthodox, a different character of much bigger families. They have more social, and usually we see that the RE in the ultra-Orthodox society, and also we have the Arabs, which has a different behavior. And we can really saw that the RE as a function of time in the general population, in the ultra-Orthodox population, and the Arab population were not the same. We had a different, we know that we can do that, but actually we found that taking a mean RE, if we want to model the spreading in Israel, was good enough in that sense. We were really able to predict the spreading and of the virus without doing that. And what I want to see actually is to, I want to go here, for example. This is a real data, okay? This is a different R for different age groups. And what's the big advantage of the model is since I'm working with particle, each particle has a name, and the name is age. So when I vaccinated people in the model, I vaccinated them by age. And now when I'm thinking of a person, looking on a person in the simulation, I know how old is he. And what I want to see now, if my simulation fits the same behavior of R in the general, because this is a big advantage of the model. The information is already there. I don't have to add a different layer of information. So we have to add another layer, and then we need to see how it interacts with the different population. All the information is already there. The only thing that I had to do is say, okay, I have a particle, each of them has a number, the number is his age, and that's all.
Okay, thank you very much. But Perhaps I will also talk with Francesco, because there are some interesting things with your model that it looks very, very nice. So I would like to see if there are some extensions.
The model can be used for, you know, for
I cannot hear you.
Italy,
I'm sorry.
and I think that the model can be extended. Ah, you cannot hear me. Okay. I don't know why. And now?
Better. Okay, no. Okay.
You can hear me?
Yes.
No?
Yes.
No?
Yeah, I can hear you. Yes.
Ah, okay. Yeah, I think that the model can be really easily be extended to any country in that sense, because the vaccinated rates are just here. I took it as, I think there's a name to it, but no, I don't think it's going to be a problem to use it for predicting how Italy, for example, can plan.
Yes, absolutely. Because so we have a small project funded by the University of Trento, and well, basically what you already did with your model, you and Francesco, is absolutely in line with what we planned, and so it might be interesting to talk if you are interested.
So an old model in the 3 paper already online with the affiliation of the university. In that sense.
No, I know. Well, okay, now there are some connection problems.
Just email me. Yeah, just email me. In that sense, yeah.
Okay, good. Thank you.
Okay. You're welcome.
If there are no more questions.
And if anyone is interested, all are.
Okay, so thank you, Hilla, very much. And I suppose we can move on to other ECT Star business.